Thanks. So the title of this talk is Ribet's theorem, and I'll hope to get to that, but first I want to give a little bit more on Sayre's conjecture, in particular the recipe for the level and the weight. And also people ask me what Sayre's conjecture is good for, and so I'll show you how it gives very elegant proof of Fermat's last theorem. So let's recall that what Sayre's conjecture concerns. It concerns a representation of the Galois group of Q into the group GL2 of E, where E is some finite field of characteristic P. The conditions I wish to impose, just to simplify things slightly, the first condition is just to simplify things, is that this is absolutely irreducible. So it constitutes what Barry would call a good candidate for a residual representation. And the second condition is essential, which is that the behavior of complex conjugation has determinant -1. So you can write it. So it has one eigenvalue of +1 and one eigenvalue of -1. That doesn't mean anything in characteristic 2, and so there's no hypothesis in characteristic 2. But other than that, you insist that the determinant of rho of the Frobenius at infinity is equal to -1. And so Sayre hopes to give a parameterization of these representations using modular forms, and from the local behavior, I should say, in fact, the whole determinant of rho is a character of the Galois group. As Barry pointed out, we know a lot about characters of the Galois group by class field theory. It can be written as epsilon times omega to the kappa -1, where omega is the Teichmuller character, which is a tamely ramified character at P, giving the action on Pth roots of unity, and epsilon is a character, Dirichlet character, which is unramified at P. And since the Teichmuller character of the Galois group of Q bar over Q has order P -1, this exponent kappa is just defined in Z mod P -1 of Z. So Sayre's conjecture is there exists a modular form, or an eigenform, F in M, K, N, epsilon, where this means weight K, level N for gamma 1 of N, and character epsilon with coefficients in E, such that rho is equal to rho F. When I write equal, I mean equivalent, conjugate inside of GL2E. So that rho is equal to rho F. That's the crude conjecture. And moreover, there's a specification for the minimal level and the minimal weight. And kappa, the K, the weight, is congruent to kappa mod P -1. Epsilon is this epsilon, thought of now as a Dirichlet character, not as a character of the Galois group of Q, but those can be identified by class field theory. And the minimal weight will always be between 1 and P squared -1, and N is, as I said, the Artin conductor. So I have to define these, what the minimal weight is and what the Artin conductor is. Now this is all done beautifully in Sayre's paper in Duke Math Journal. However, the recipe for the weight is fairly complicated, and it might help more to show you where that recipe comes from than to give you the exact recipe, which you can go to the paper to find. So I'll recall for you, at least I argued, although I didn't give the connection, that when you constructed rho F of the representation of Deligne for weight less than or equal to P +1 occurred as a subrepresentation on the P torsion, occurs in the P torsion of the Jacobian of J1 of NP. If the weight is less than or equal to 2, it's actually in J1 of N, but it's always in J1 of NP for this weight. And from facts about the study of the torsion on that Jacobian, you can deduce local properties of this representation rho F. In particular, that's how Sayre was going to guess what weight it came from. And these local properties were deduced from a careful study of this Jacobian by Deligne and by Serre, by Fontaine, by Tate. And I'll just tell you what they are. So we're going to study the restriction of rho f to a subgroup of the Galois group of q bar over q, the decomposition group at P. Maybe I'll call that D. The Galois group of qp bar over qp, which is a subgroup well defined up to conjugation in that Galois group. And to tell you what it looks like, I have to recall that there's a filtration of this group, a three-step filtration. It has a normal subgroup. The decomposition group at P has a normal subgroup, the inertia group. And then that has a normal subgroup, which is in fact normal in D, which is its P-CeLO subgroup turns out to be normal, called the wild inertia group. And if you remember your diagram of fields to give you this filtration, if you take QP, you can go, before you get to the absolute Galois closure, you can take the unramified closure, you can take the tamely ramified closure, and then you can take the algebraic closure. P, which is the most interesting part of the group, is the subgroup that fixes the maximal tamely ramified extension. I is the subgroup that fixes the maximal unramified extension. So this quotient, this Galois group here is I mod P, and this group here is D mod I. And P is is the most interesting part of the group. As I say, it's this huge pro-P group. But these two quotients are well understood. This is the Galois group of the algebraic closure of the field of P elements. So it's isomorphic to procyclic group Z hat. And this group is also procyclic, but it has no elements of order P, because the tamely ramified extension means of degree prime to P. And in fact, there's a canonical isomorphism of this group with the inverse limit of all the finite field extensions. And this is even true not only as a group, but as a module over this group. Namely, Frobenius acts on this inverse limit by raising to the pth power. So this is a procyclic group, but it's the product of all the ZLs with L not equal to P. And then this is a very mysterious group. Okay, now the restriction to the decomposition group at P, assuming, let's assume two things. First of all, that the weight of F, so the weight K of F, is less than or equal to P plus 1. Secondly, when I talk about the weight, I'm assuming that it's the minimal weight. Namely, you might have something of weight P plus 1. You might have weight of F is equal to P plus 1. But then F might be of the form the Hasse invariant times G, where this has weight 2. Right? The Hasse invariant has Q expansion 1. So this doesn't change the Q expansion. F and G would have exactly the same Q expansion. And since this Galois representation associated to F is determined by the coefficients of the Q expansion, these would give the same representation. So I would not consider this F to have weight P plus 1. I'd really say that its minimal weight was 2. If, say, the weight is 2. This is, in the language of modular forms mod P, this is called the filtration, but I'm not going into this. And the only other case where you could have a lower filtration is if the weight of F is equal to P, and F is equal to A times G. With this of weight 1, I would say the weight is equal to 1. So I'm talking about a form of weight less than or equal to P plus 1, but if it's divisible by the Hasse invariant, put it at the lowest weight you can. Okay, now I can tell you what the local behavior of Deligne's representation is at P. All right, the first condition is, let me switch boards here. I set this up. Let's see if I do it right. Good. A little more down here. Whoops. Okay. The first possibility is you restrict the representation not to the whole decomposition group, but to the wild inertia group. Now, the wild inertia group is a P group, and you're having it acting in characteristic P. So it fixes something, fixes a line. Now, it might act trivially on the entire space, but let's suppose that it acts non-trivially. So case 1 is P acts non-trivially. on this vector space V, which is this two-dimensional space over E that the Galois group is acting on. Well, then it fixes a unique line, because it fixes some line. And since it's a normal subgroup in D, D fixes that line too, and so does I. So if we restrict the representation to the inertia group, it ends up in a Borel subgroup, and in fact the entire decomposition group ends up in a Borel subgroup. D maps to a Borel subgroup of GL2, fixing the line fixed by the wild inertia. And then if you restrict the representation to the inertia group, you find that it has to look as follows. For these weights k less than or equal to p plus 1 as usual, it turns out to be a power of the Teichmuller character, in fact the k minus first power, 0. So on the line that it fixed, it acts it by this. And then the rest you can almost work out by the determinant, because the determinant on the decomposition group is the power of this Teichmuller character times an unramified character. And then the wild inertia acts non-trivially there because it didn't fix the entire space. So the inertia group is mapped via these two characters of the tame inertia and a non-trivial character of the wild inertia. And the k is exactly this k. So that's the theorem that you prove about this local representation. This is rho f, of course, for a modular form of weight k. However, this case only occurs if the weight is between 2 and p plus 1. Namely, if the weight is 1, we're going to see that p acts trivially on v. So you don't get this case. Now, the beautiful thing about this is that you notice that for all these different weights, this local representation almost tells you what the weight is, because these powers are different powers for all the k's between 2 and p plus 1. There's only one possibility of confusion, and that is between k equal 2 and k equal p plus 1, where this power is just the first power of omega. So if k is equal to 2 or p plus 1, then you get the inertia group acting through this representation. And it looks exactly the same. And how would I know from the local representation whether it came from weight 2 or whether it came from weight p plus 1? Well, Sayre figured this out too. In this case, you have to look not just at the action of the tame inertia group, you have to look at the action of the wild inertia group. Namely, the wild inertia group is just acting, remember, non-trivially. We assume that it's going to this, it's acting in this way. So this gives a homomorphism from the wild inertia group to the additive group of E, which is a group of type P, 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 P. So it gives a bunch of characters of order P of the wild inertia group. Now, if you look at the wild inertia group, it's the Galois group of q bar over qp tamely ramified. And qp tamely ramified contains the pth roots of unity. So this is a Kummer extension of qp tamely ramified. It's gotten by taking pth roots of things. Okay? Now it turns out that if this representation comes from weight 2, namely this bottom part, then these characters of wild inertia come from taking the pth roots of units. So in this case, star comes from extensions of the form the pth root of units. And in the case where the weight is really p plus 1 and it's not divisible by a, so it doesn't go back to weight 2, then this extension of the wild inertia group comes from taking the pth roots of elements whose valuation is not divisible by p, so it cannot be turned into units. That's the situation that Sayre calls très ramifié. So this is a situation that Sayre calls peu ramifié. And then in the case of weight p plus 1, this star comes from the things that look like this p times a unit, pth root of p times a unit, and that's what's called très ramifié. So just by looking at the local representation, we can tell what weight it came from. In all cases except for 2 and p plus 1, we can tell it from the characters of the tame inertia group, and in those two cases it's distinguished by the action of the wild inertia group. The conductor of these très ramifié representations is much higher than it is for the peu ramifié. Okay, that's a subtle point. Now let's take a look at the case where p acts trivially. So the second case is case 2, P acts trivially on V. Well, in that case, the image of the inertia group, because P acts trivially, the image of the inertia group is either a torus or it's either in a torus or it's contained in the normalizer of a torus. In the first case, the inertia group goes to characters of the following form, same k minus 1, but now P is acting trivially. And here, this can only occur for from 1 less than or equal to k less than or equal to P minus 1. Namely, k equal P and P plus 1 don't occur in this situation. And in the second case, when it goes to the normalizer of a torus, then if you look at the action of the inertia group and you diagonalize it, you get the two characters that Tate called the fundamental characters of level 2 or whatever to the k minus first power. Where phi 1 and phi 2, if you view I mod P, which is what it's acting on as the projective limit of the finite fields, these are homomorphisms from the quotient fp squared star to fp squared star, and phi 1 and phi 2 are the two field homomorphisms. So these are the fundamental characters. And again, this occurs only for weights 1 less than or equal to k less than or equal to p. And in both cases, you'll find that the actual restriction to the inertia determines what k is in this case, because we don't go up here to p plus 1 or p. And consequently, this is the way Serre's conjecture develops. You take your arbitrary representation, which I've erased, of course, and you restrict it to the inertia group at p. Now, suppose you find that you're in one of these situations, one of these three situations, namely where the restriction to the inertia group at p either is in a Borel with a fixed action on the quotient, or has a fixed action on the quotient, or is the same powers of the two fundamental characters. Then the weight is less than or equal to p plus 1 and is given by this recipe. Namely, you look at what power you have and you find the correct k in the interval with that power. If the restriction is not of that form, but then you'll find that it's a twist of this form by a power of the Teichmuller character, and you can work it out what the weight is from the action of the theta operator on the space of modular forms. I'm not going to do that. That's why the recipe becomes so complicated. But if you get one of these restrictions to decomposition group at p, which are the simplest ones, then the weight in Serre's conjecture will be less than or equal to p plus 1 and will be determined by the power, except in this weird case where you have to look at the action of the wild inertia. So that's in some sense the recipe for the weight. Look at there's one case that's very amusing. When will the inertia group act trivially? When will the inertia group act trivially? Namely, when will the representation be unramified at p? Well, not in this case, because the wild inertia group's acting non-trivially. But over here, if k is equal to 1, or if k is equal to 1 here, so you get the 0th power, the inertia group acts trivially. And that's the only case. So one of the predictions of Serre's conjecture is the predicted weight k is equal to 1 if and only if rho is unramified at p. Another prediction. When is the weight equal to 2? When is the predicted weight equal to 2? Well, let's write it down. Predicted weight is equal to 2 if and only if, well, it's not unramified, but look at the restriction to a decomposition group at p. Namely, if we restrict to the inertia group at p, it can be of the form omega 1 star. It can be of the form omega, where star is per ramifié, whatever that means. It can be omega 1, or it can be phi prime. Those are the three situations that would give you a weight 2. Now, Serre recognized these situations. This is exactly the situation where the representation of the Galois group comes from the general fiber of a flat group scheme of E vector spaces over ZP, which is not purely multiplicative or purely étal. So let me write that down. So this is, remember we had that theorem in Tate's lecture. Raynaud showed that at least for p greater than 2, so I'll write it down for p greater than 2. So this is if and only if p greater than 2, the representation of the Galois group QP bar or QP on V is the general fiber of a flat group scheme, actually of E vector spaces, E vector space scheme, over ZP, not purely multiplicative or étal. The case weight 1 is the case where it's the general fiber of an étal group scheme. That's where it's unramified at P. But you see, this is the case where you have an extension of mu P by Z mod P, or a twist of that. Here's another. And this is the case where you have the flat group scheme coming from P torsion on a, say, supersingular elliptic curve. So these are exactly the characters that can come up in Raynaud's theory, and the fact that this is per ramifié is exactly what you need to show that this extension exists over ZP. So this is a nice condition for the weight, predicted weight. So we'll have this condition a lot in later lectures. I think it's called flat. Okay, and now I just want to say a very brief word about the predicted level, because I said it was the Artin conductor. I don't want to review all of ramification theory and local class field theory. This is exactly the way you define the conductor of complex representation of a local Galois group. So at primes L, for prime L not equal to P, we define an integer NL of rho, which is greater than or equal to 0. As the Artin conductor, you can, this is equal to the dimension of the space of Hams over I of the representation V and the Artin representation. But that doesn't define the Artin representation. Another way of doing it is it's a sum from I greater than or equal to 0, 1 over I0 mod II of the dimension of V mod VII, where the I's are the filtration, the lower filtration of the inertia group. So I0 is equal to I. I'm now thinking of this as an inertia group of a finite extension because, after all, this homomorphism is continuous, so it factors through the Galois group of a finite extension of QP, and then that has a normal subgroup I1, which is P, and then P has a further filtration by the higher ramification groups. And when you calculate this, Artin proved it's an integer, and in fact it's multiplicity of V in a certain representation. And the important, then you define N, this real integer, which is prime to P, to be the product over all L not equal to P of L to the N L rho. And that's the Artin conductor. Now the properties of this that we're going to need are not too serious. The main thing is that NL is equal to 0 if and only if V is unramified at L. And if it's tamely ramified, i.e. the wild inertia group I1 acts trivially, then it's equal to the dimension of V modulo V of I. But the first thing is the main thing. So that this number is prime to L if and only if it's unramified. So let me just say that. The predicted N is prime to L if and only if rho is unramified at L, which is true for almost all L. And this guess of Serre's comes from work of Carayol, which shows that that if you construct Deligne's representation rho F from a modular form on gamma 1 of N, that this Artin conductor divides N. So it's certainly a reasonable guess. Okay, so those are the local invariants of the representation. Now, I said that I would show you how those local invariants led Serre to a very nice and elegant proof of Fermat's last theorem, which motivated all the rest of the stuff. So here's how that goes. It not only applies to prove that there are no solutions of Fermat's equation, but many similar equations, very flexible method, because what Serre is giving here, if you believe the conjecture, is a complete description of all these extensions with Galois group GL2 of a certain type, and those are going to come up in many situations in number theory, and frequently you'll be able to show that there's no modular form, so that the extension shouldn't exist. So let's do Fermat. So we start off. Let's assume that our prime P that we're trying to prove Fermat's last theorem for is at least 5. Actually, I want to assume it's at least 7. I'm cheating, but we'll assume that we've proved it for small primes P. And on the other hand, we somehow or another have found a solution of this equation where A, B, and C are integers, and A, B, C is not equal to 0. And we can assume, of course, that they're relatively prime by dividing through by any common factor, and consequently they can't all be even, they can't all be odd either, so let's let B be the even one, so we assume B is even, and in particular B to the P is congruent to 0, at least mod 2 to the 7th, which is all we'll need. And then, as I say, they can't all be even, so one of them has to be, in fact, A and C then have to be odd, and you'll also see that since this is divisible by 4, they can't both be 1 mod 4, so one of them has to be 3 mod 4, so we'll set A to be the one that's congruent to 3 mod 4. And with that normalization, we define the Frey curve, which I'm sure people have seen a lot of. It's this elliptic curve associated to the solution in the Fermat equation, x minus A to the P, x plus B to the P. And it's an elliptic curve. And the reason it's an elliptic curve is when you calculate its discriminant, that these roots of this equation are all distinct. And in fact, the discriminant turns out to be, if I did it right, 2 to the 4th times ABC to the 2p power. It's not quite the minimal discriminant. You can make it a little bit better at 2, but that's about all you can do. The minimal discriminant turns out to be delta divided by 2 to the 12th, which is still an integer. Okay, now this is non-zero, my hypothesis. On the other hand, when you can calculate the conductor of this elliptic curve, the conductor has to do with at least away from 2, where these roots come together, and you'll get 1 power dividing the conductor at every prime L, where 2 of the roots come together, and more than that, where 3 of the roots come together. Well, you don't have 3 of the roots coming together by our hypothesis. So you find that the conductor of this curve is just the product of all the primes L dividing ABC of L to the first power. In particular, this curve is what's called semi-stable, has good reduction as it could. And we can now distinguish the first and second cases of Fermat's last theorem depending on whether P divides A, B, and C as to whether this curve has good reduction at P or not, if you like that. Okay. Now, what you want to prove, of course, is that this elliptic curve doesn't exist. It's too good to exist. So one method that was attempted was to say, well, look, the discriminant is such a big it's at least the 2p power of the conductor. That should go wrong. And that's probably a good reason why it shouldn't exist, except nobody can prove that. It can't happen for an elliptic curve over the rationals. However, Serre's idea is to prove it doesn't exist by constructing a number field that doesn't exist, namely by taking the extension of the rational numbers that you get by adjoining the p torsion on this elliptic curve, which is a finite group scheme of order p squared, any elliptic curve. Sorry, better not call this elliptic curve E because I've been using E for the field, so this would be AP. And my hypothesis that the curve is semi-stable and the prime's at least 7 applies by very general results of Serre and Mazur that this is really an extension of where the Galois group is GL2 of P. It's as large as it can be. And so you get a two-dimensional representation from the p torsion on the Frey curve, where p is the same prime as the exponent of the Galois group of Q. So gives a rho from Galois group of Q bar over Q into GL2P. And you find that the determinant of this representation is just the Teichmuller character, omega. That's true for any p torsion on any elliptic curve. And consequently, this has the right property for the action of complex conjugation because this is an odd Dirichlet character. And it's also absolutely irreducible. So this should be on Serre's list. Some modular form F mod P. That's Serre's conjecture. Okay, now we have to go calculate what is the predicted level for F and what is the predicted weight. Now, usually, you'd expect the primes in the conductor of the curve to divide the level of the form mod P. But this is a miracle situation. The reason this is a miracle situation is, first of all, the primes in the conductor divide the conductor to the first power, so it's semi-stable, and Tate gave a local description of such elliptic curves. And you can show that if you adjoin the p torsion on a Tate elliptic curve, that it turns out to be unramified at the prime, provided the ord L of delta is divisible by p. So it turns out that the p torsion is locally unramified at L if and only if ord L of delta is congruent to 0 mod P. That's an argument due to Tate, where he gives the explicit description of the torsion on his local elliptic curves. Well, that's true for all primes L except for 2. Because if you look at ord L of delta, L divides this, but here you have a 2pth power. So this is all L not equal to 2. And moreover, you find that the p torsion, same argument works at p. You have to be a little bit more careful, but Tate does it also, is locally flat at p, same condition, ord p of delta congruent to 0 mod p. And that's true also because p is not equal to 2. So what is the Serre conjectured conductor? Well, it's primed to everything except for 2, and at 2 it's just 2. So the conductor that predicted n is equal to 2. And what's the predicted weight? Well, the predicted weight k is also equal to 2 because it's flat at p. So flat at p is when you predict weight 2. So Serre says that this is equal to rho f for a form of weight 2 on gamma 1 of 2. Right? But then you go calculate the space of forms of weight 2 on gamma 1 of 2. It's a non-trivial space, but they're all Eisenstein series, and none of them give irreducible representations of this sort. So there are no such representations. Representations rho f. And consequently, if you believe Serre's conjecture, this representation doesn't exist. In particular, this number field doesn't exist. And by that matter, the poor Frey curve couldn't exist, and then by that matter, the poor solution of this equation couldn't have existed. Okay. So that's, as I say, a very elegant one-board proof. Now, that's not how the proof went, because we don't understand yet why Serre's conjecture is true. However, the proof exploits the proof that's been given, it exploits a key thing about this particular two-dimensional representation mod p, is that it comes from the p torsion of an elliptic curve. Right? So let me at least state Ribet's theorem, and then I'll tell you the detour that was taken to the proof. Let's see if I can do this. Down, here, up here. Good. Got it. Uh-huh. No. Is this? No. So Ribet's theorem is a particular case of this prediction here. This unramified at L prediction. And checks it in a very crucial case. So let me state his theorem this way. He has generalized it to a much more general setting, and then Diamond has also made some generalizations, but this will suffice for us. So we assume P is greater than or equal to 3, our residue characteristic, and that we have an F, an eigenform, mod P, of weight k equal to character epsilon is equal to 1, like this situation here, and level n times L, where L is some prime. In this situation, it's not P, but I'll talk about the case when it is P in a minute. But at least it's prime to n. Okay, so from that we get a Galois representation using Deligne. The second assumption is, assume that rho f is irreducible. I should have said that when P is at least 3, irreducible and absolutely irreducible are the same thing, because you have Frobenius at infinity. It's irreducible and unramified at L. So for some miracle reason, it turns out to be unramified at L. Then Serre conjectures that there's another eigenform whose level is prime to L and gives rise to this representation, right? Because if it's unramified at L, the exponent of the conductor should be 0 and not 1. And that's what Ribet proves. Then rho f is equal to rho g for an eigenform G mod P of weight k, weight 2, character 1, and level n. Namely, he gets the L out, as predicted by Serre. So that's the theorem. So this is truly remarkable because if you look at the definitions of the spaces of modular forms mod P of level n and level NL, they have almost nothing to do with each other. And yeah, of course, the general thing, which is starting from level NL, will not give a representation which is unramified at L. So it's a very special hypothesis. Okay, so let's assume this theorem, and now I can walk you through the detour that was made in the proof. You'll see in some sense how bizarre it looks when you do it this way, because you get involved in all kinds of things that don't look like they're relevant. So the proof of Fermat looks like this. You start with the solution ABC, again goes to the Frey curve A, and now it's an elliptic curve, a semi-stable curve. By a consideration of the fact we forget about its representation on its p torsion, we look at the representation on its 3 torsion. And by Langlands, the representation on its 3 torsion is modular. Providing it's irreducible. But in fact, Elke showed that once you have the Frey curve, even this argument at 5 is unnecessary. Since you have all the 2 torsion, the 3 torsion representation has to be irreducible. Rho 3 is modular. Then by this argument of Taylor and Wiles, we lift it all the way up to the 3-adic representation is modular. So the 3-adic representation is modular. So E is a modular curve of level n. That's the part by Taylor-Wiles, which you'll hear a lot about next week. And then, since the elliptic curve is modular, we find that its p torsion representations are modular of level n for any prime p. So that then implies that the rho p is modular for all p, but of course of level n, which is the product of the weight k, weight 2, level n, which is the product of L dividing ABC of L. However, we know by Tate's work that it's unramified at all of these primes except for 2 and flat at the prime p. And so Ribet's theorem allows us to at least conclude, at least in the first case, I'll say that. So then by Ribet, we get that rho p is equal to rho g for g modular of weight 2 on gamma 1 of 2, and epsilon is equal to 1. And then you show that this couldn't exist. Then the argument ends in the same way. But somehow we get that the crude conjecture of Sayre is true. It's modular somewhere, not by a consideration of the p torsion on the curve, but a consideration of the 3 torsion through the miracle of the solvability of this group GL2 of 3, which Tunnel has no doubt talked to you about. I should have said that this is not the full strength of Ribet's theorem, because this only deals, the way I've stated it for modular forms mod p, it only deals with primes that are in the level. Namely, it doesn't deal with the question of the weight. And if p, maybe I should have said this, if p divided n here, then it would be a modular form mod p of level n over p, but the weight would be a priori p plus 1. However, Ribet's theorem for L equal p says that if rho f is irreducible and of weight p plus 1 and is flat at p, which is the analog of unramified for p, then it's equal to rho g for something of weight 2. So the prime L you remove from the level, and if you want to do the p case, Ribet's theorem says if you start off with something a priori of weight p plus 1, but it's flat at p, which is the analog of unramified, then you get down to something of weight 2. I'm not going to deal with that case, although that turns out to be one of the easy cases in the proof. The hard part of the proof are the primes that are not equal to p. So now I'm going to try to wave my hands a little at the proof. Oops. No, stop that one. Okay. God. Okay, the proof has 3 steps, at least as I understand it. The first step I may actually do. Okay, so the step 1 is the case where L is not congruent to 1 mod p. These turn out to be the easiest primes to get out of the level if they're unramified. In particular, L equal p works here, and with the weight argument. Now, the argument in this case is due to Mazur. It's somehow called Mazur's principle. And I'll sketch that for you in a second. Let me just put up the other 2 steps. Step 2, now the difficulty arises. You'll see this argument falls apart miserably when L is 1 mod p. So it was a real question how to deal with those primes. So the step 2 is a step backwards, which is that you don't try to pull a prime out of the level, you put a prime back in the level. So the step 2 is something that Ribet had worked on earlier. You increase the level from NL to NLQ, where Q is a completely new auxiliary prime, which is not congruent to 1 mod p. And you want something which is of weight 2 and is new at Q. Now, I should say that this increasing of the level business, as intricate as it is and as beautiful as it is in general theory, is not necessary for the proof of Fermat. Because in the Fermat case, you have sitting around at your disposal already this auxiliary prime. namely q equal 2. Q equal 2 is sitting there a whole time, so there's always another prime besides L in the level where the form is due at q and does not satisfy congruent to 1 mod p. So if you just want it for Fermat, which is short-sighted, I think, you don't need step 2. However, this is not always possible, by the way. Ribet made an analysis of when it's possible, and it's possible if and only if possible if and only if the Frobenius at q, which in this Gower representation is, of course, unramified at q, so you want that rho f of the Frobenius at q has an eigenvalue either equal to 1 or equal to minus 1. That turns out that it's easy to see that this is a necessary condition for increasing the level, and the theorem is that it's sufficient. And how do you know that there are primes which are not congruent to 1 mod p which have such an eigenvalue? Well, the standard example of such primes that Ribet and the people who follow his arguments use is to take, e.g., take q such that rho of the Frobenius at q is conjugate to rho of the Frobenius at infinity in GL2 of E. Remember, we assume the Frobenius at infinity had eigenvalues plus 1, minus 1. Here we just need either an eigenvalue of 1 or minus 1. I mean, why not give it to them both? This is a well-defined conjugacy class in this group by the Chebotarev density theorem. There are an infinite number of such primes, right? And the characteristic polynomial of them is just x squared, just x squared plus 1. On the other hand, that's got to be x squared plus q, right, mod p. And so, oh, that's the wrong way. Let's try it again. The determinant is on the one hand minus 1, and on the one hand it's q. So the determinant here, determinant of the Frobenius at infinity is equal to minus 1. On the other hand, the determinant of the Frobenius at q is congruent to q. And so these q have the property that q is congruent to minus 1 mod p. And since p is not 2, they satisfy all the conditions. And there are an infinite number of primes q where you can pop the level up. Now, why would you want to do that? Because then there's an amazingly intricate argument. Once you have these 2 primes in the level, you then introduce a Shimura curve associated to the quaternion algebra ramified at both L and Q. Associated to the indefinite quaternion algebra ramified. You need 2 primes for this, L and Q, and to get level n, you take an Eichler order at n. And by a detailed study of the reduction of the Shimura curve, which is a very great elaboration of step 1 that I'm going to show you, Ribet's able to show that, in fact, this modular form, which occurs at level NLQ, in fact, gives a Gower, there's another modular form congruent to it at level NL to show rho f is equal to rho h for h of level, NQ. And then we pull q out using step 1 because q is not congruent to 1 mod p. So somehow you take a step back to go 2 steps forward. Let me try to do step 1 and you'll see what a business this becomes. Oops, stop. Up. Now, which one is this? Stop. Stop. Now, to do this, I have to introduce some ideals in the Heck algebra. Because this approach is very much influenced by Mazur's point of view in his paper on the Eisenstein ideal, which I think is fundamental to this whole subject. And that approach uses the ideal theory of the Heck algebra in a heavy way, and the relation with modular forms mod p is very pretty. So we have this thing modular. So recall that f is of weight 2 and level in L. And in particular, it occurs in the Jacobian. Rho f occurs inside of the torsion. It occurs in fact, J0 of NL, the Jacobian of X0 of NL, the P torsion. That's a Galois module, and this is a simple submodule of it over E. Okay, now how do we refine this slightly? Well, the way we refine it slightly is we define an algebra of endomorphisms of J0 of NL. So we let T, the Heck algebra of endomorphisms of J0 of NL. They're all defined over Q, which is generated over Z by the, oh boy, well, I have to use even another letter, by the T's and the U's, and you don't need the brackets. Namely, you get the T's for primes not dividing NL, you get the U's for primes dividing NL, and then there are no bracket operations because we're in X0 and not in X1. Okay. Now, the way you prove that this occurs in the P torsion is you first prove that it occurs in the tangent space of the Jacobian mod P. And the tangent space of the Jacobian mod P is a faithful module for T mod PT. Acts faithfully on the modular forms of weight 2, mod P, in fact on the cusp forms of weight 2, if I wrote it that way, for gamma 0 of n. Because this is the cotangent space of the Jacobian in characteristic P, and the endomorphisms, at least mod P, are faithfully represented on that space. We have an eigenform in here, whoops, and L. There we go. We have an eigenform F in here, an eigenform for the Hecke operators. So that gives us a certain ideal, a maximal ideal of T mod PT, on which the associated quotient algebra is acting through the eigenvalues. So the eigenform F defines a maximal ideal M, well, of T mod P, but also of T, where it contains PT. So it's an ideal of characteristic P. And you can think of this as being generated by P and all the differences, P, and all the differences, well, since I've used every prime, I think I'm dead. P, TQ minus AQ. So it's generated by these differences because those are exactly the things that annihilate this eigenform. And the T mod M, of course, is our finite field E. So modular forms mod P, and in this perspective, give rise to maximal ideals in the Hecke algebra. And in fact, you can show this representation not only occurs in the P torsion, but in the submodule of the P torsion annihilated by M, because that's a submodule. And a lot of study has been given to what the rank of this module is as a module over E, and typically it has dimension 2, namely just realizes rho f in the nice situations. All right. So we put our representation inside of this. Namely, we have an inclusion of Galois modules. This is a map of Gal Q bar over Q modules. Well, that would be true for any F. Now we have to somehow exploit the hypothesis that this representation is unramified at L. And this is what becomes quite tricky. Namely, there is this abelian variety has bad reduction at L. However, there's a model for it over ZL, which I'll call J, the so-called Nerone model, or J0 of NL over ZL. So it's the best possible reduction model. It has bad reduction. We'll have to take a look at its reduction. And we let J bar be the reduction, or the special fiber of this, over Z mod LZ. Now this is a commutative algebraic group, but needn't be connected, and it certainly isn't an abelian variety. And it's known, because this is semi-stable at L, that at least its unipotent radical is 0. That's at least good something. So there's two-step filtration of J bar. First of all, you have its connected component. Call it J bar 0. And then that maps to a finite abelian group of connected components. Connected component group. And it turns out that this connected component of J bar, as I said, has no unipotent radical. That's because exactly 1 power of L divides the conductor of this. And therefore, it's what's called a semi-abelian variety, an extension of an abelian variety by a torus. So the J0 bar has a kernel, which is the toric part. And the quotient is an abelian variety. And what abelian variety it is? Well, miraculously, this abelian variety is isomorphic to J0 of n squared. So that's a consequence of the reduction theory of this modular curve x0 of nl at the prime L due to Deline and Rappaport. That's an abelian variety. Okay. Now, the first thing that Ribet uses is a nice property of the Nerone model that says if you have a map from a Gal Q bar over Q module, that would be a group scheme over Q, a finite group scheme over Q, into the Jacobian, which is another group scheme over Q. And this extends to a flat group scheme over ZL, then it extends to give a model from this flat group scheme over ZL into the Nerone model. And moreover, it reduces injectively into the Nerone model mod L. But that's exactly what we have, because the hypothesis, which I've erased, that this representation is unramified at L is exactly what says that this comes from a finite flat group scheme over ZL. Here L is prime to P, so extension to a finite flat group scheme means extension to an étal group scheme, so that it extends to a G uniquely by the étal theory over ZL. We get an embedding of, in fact, an immersion of G into J. And when you reduce it, you actually get an embedding of this module into the P torsion on the Jacobian mod L. So reduction, and that's the use of the hypothesis. Gives an embedding of V into J tensor Z mod LZ over, and you could take the M torsion on this, you see, because M is an ideal for the Hecke algebra, and even though the Galois group of Q bar over Q no longer acts on the reduction mod L, the only thing acting is Frobenius at L, you still have the action of the Hecke operators, and you check that if this extends and reduces, then it embeds into the M torsion here. This is non-zero and gives a copy of V. Good. So we have V somewhere. Now the idea is somehow or another to torture it through this sequence and eventually produce an embedding of this Hecke module into the P torsion of this abelian variety. Because if we could embed this specific Hecke module, associated to the ideal M, into this abelian variety, then taking the M torsion, etc., would give us this representation rho G associated to a modular form of level n in weight 2, because things of weight 2 and level n will come from the P torsion of this abelian variety. So if we could just show that somehow the Hecke module coming from the M torsion survives all the way to here, then we'd have lowered the level. Okay, well, first thing we want to show is that the Hecke module appears here and not in here. Why can't it appear in the connected component group? Well, Ribet does an analysis of the connected component group, and he shows that on the group of connected components, I'm a little nervous about P equal 3 here, but I'll try it. Okay, on the group of connected components, the L Hecke operator or the Q Hecke operator acts as 1 plus Q. And So it's annihilated by this ideal. Now this cannot be the ideal M because this ideal is what's called the Eisenstein ideal in Mazur's paper, and it gives rise to a reducible Galois representation, and we assumed in Ribet's theorem that the representation was absolutely irreducible. So the action of the Heck operators on the component group shows that the ideal M cannot appear here in the support of this module, and consequently the ideal M appears in the support of this module. Good. Now we're down to here. Why can't the ideal M appear in the support of this module, in the torsion on that module? Well, there Ribet has to work out what that torus is. So this is all very delicate theory because we're reducing the abelian variety at a prime where it has bad reduction. However, one knows something about that torus. In particular, it's almost split. It's split over a quadratic extension. Frobenius et al. Acts on it on its p torsion points on T, the p torsion. Frobenius et al., which is the one thing that's still acting, acts either by plus or minus L. Plus L if it's in the split part of the torus, minus L if it's in the part that becomes split over a quadratic extension. And in fact, since we're in a simple submodule of the p torsion of the torus, it has to act either as plus L or minus L. And since we're in a rank 2 module, so on V, we get the determinant of Frobenius et al. On V is equal to L squared. Because if it's plus L and you take 2 copies, you get L squared. And if it's minus L and you take 2 copies, you also get L squared. On the other hand, we know, so if V occurs in the p torsion. On the other hand, we happen to know that the determinant, but we know, that's the one thing we still have, that the determinant of Frobenius L on V is equal to L. That was by the construction of this representation V sub f, or whatever. And consequently, it could not occur in the torus if L is not equal to L squared mod P. Hence, if L is not congruent to L squared mod P, V does not occur in the p torsion of T, and it occurs in the p torsion of this abelian variety, and from that you construct the desired eigenform. On the other hand, if L is congruent to 1 mod L, then L could be equal to L squared. No problem there. We get no contradiction from that. And it's quite mysterious what's going on. I mean, I think in that case V can occur in the p torsion of T. It's just that it occurs again somehow mysteriously here. It's a non-semi-simple thing. So it really looks like, when you look at this proof, you can't imagine what would happen in the case when L is congruent to 1 mod P. But this miracle of the bad reduction of the Schmor curves, which is an amazing elaboration of this argument of the tori and their character groups and the component groups, still gets you through. So this is undoubtedly the main thing that's been done on Serre's conjecture, this lowering of the level just by 1 prime at the unramified case. It shows how delicate the whole theory is of modular forms mod P. But I hope I was at least able to give you some idea of what was happening. Thanks.